Hello everyone! Today's presentation is about Bayesian dynamic linear models for time series data analysis. My name is Sherwin and this presentation is a part of the course Large Scale Data Analysis and Decision Making at HEC Montreal. Let's start by the presentation structure. This presentation is divided in 5 sections, as you can see on the top blue ribbon. First, I start with why. Specifically, answer the question about why do we need time series analysis. Then, I explain the state space model, which is a general concept behind BDLM. After, we go through the BDLM, and of course, we need to show examples to understand the BDLM applications. In the next section, I will show 2 case studies that uses different time series data. Also, I compare the BDLM results with the ones from the Facebook Profit, which is a package for time series analysis. Finally, I will discuss the BDLM current research directions. Let me give you the big picture in 3 steps, which I call it the golden circle. So, if we can manifest our thoughts based on these 3 simple questions, then we can connect the objectives in a deeper level to understand the problem statement. We start by asking this question: why do we want to analyze time series? And the answer is about the importance of the time series analysis and its purposes. The next question is how we analyze a time series, and the answer is probabilistic models. Why? Because probabilistic models can quantify uncertainties. And the last question is what is the product or the tool that we're going to use? And the answer is the state space model, which leads to the Bayesian dynamic linear modeling within this presentation. And I will talk mostly about the BDLM, but it is necessary to understand the postulations behind it. Let's start with why we want to analyze time series data. First, let's define it. A time series is a sequential data collected over time, and they are often correlated to each other. We denote it by the bold small letter y, and the index t indicates the time steps. The bold y shows we have multiple observations at any time, like we have 2 different measurements from a system dynamics. If there's a single observation, y will not be bold. On the right, you see 2 time series data, and we will work on these 2 time series data during this presentation. The first data is a temperature collected over the 2 years, and the second one is called VIX or volatility index. It is an indicator of the volatility of the global market. For the better comparison, we selected the data for the same 2 years as of the temperature. There are 2 reasons for why we analyze time series data, either to explain or to predict. We want to know what's been happening, and we want to know what will happen to the system that we are collecting data from. For example, the temperature data has a periodic behavior. How does this behavior continue in the future? Or the VIX data fluctuates a lot and it has a decreasing trend. What is going on, and how can I quantify this trend and predict what will happen in future? Why this is important? Because it supports the decision makers to make rational decisions. The second question is how we will carry out such explanation and or prediction. Mathematically, our goal is to build a probabilistic model to predict y at time t given the history. In this expression, the part that is in blue is the history, and it shows that the information is going to be carried out into the future. Let's visualize it. Consider this 2-axis graph. The horizontal axis shows the time and the vertical axis shows the observation. The circles show single observation at different time. Let's pick a time such as the one associated with time t. The left data points are the past and they are in blue. The right data points are in gray and they are future, and we haven't seen them yet. The blue part is exactly the part in the expression, and it shows that we want to find the mean and confidence interval of the observation at time t given the history. Up to now, we know our why and how. Let's see what we'll use to handle this probabilistic model. We use state space models to build a probabilistic model. For this, we need to provide some assumptions. First, we use Markov property. It says the future is independent from the past given the present. Mathematically, it means that the history is reduced to only the direct previous time step. On the right, you can see it visually. The blue region is now a small segment of time. This is the place we postulate the state space model. When we have it for this region, we can repeat it for other time steps recursively. That's why I removed the blue part from the equation and you see a blue box on top of it. The second assumption is that we assume the observations have an underlying dynamic, that we cannot see them and they are hidden. We can show it mathematically as another probabilistic model, where X shows the hidden state variables. Visually, you can see a red dotted line. In the same blue region that we postulate the state space model, now it is a solid line. It means that we use the same Markov property here too. So we can build the hidden state variable X for this region, and then we can repeat the procedure for other time steps. Now let's put everything together and define the state space model's goal. The goal is to build a probabilistic model to predict the y and x at time t, given the history. Mathematically, it means that we want to build a joint probability model for both observations and hidden state variables. In other words, as we are predicting what is happening for the observations, we are explaining the dynamics of the observations too. Here, we remove the blue part to show that once we postulate for the blue region, as you saw before, we can repeat the process recursively. Now let's focus on our model. Using the probability production rule, we can decompose the model into two smaller models, observation model and transition model. The observation model tells us how the underlying dynamics can be superposed to generate the observation. And the transition model tells us how these underlying dynamics are evolving through time. Again, you see the blue part, which in fact tells us that we only focus on the small blue region, and after building our model, we can repeat the procedure for other time steps. A quick side note is going to be, like in machine learning, roughly you can decompose an unsupervised learning into the series of supervised and unsupervised learnings. Building the joint probability between the observation and the hidden state variables is an unsupervised learning. As you can see, the unsupervised learning here is decomposed into the observation model, which is a supervised learning, and another supervised learning, which is the transition model. Later, you will see that for the transition model, we will handpick the underlying dynamics according to the data engineering heuristics. For example, whether we want to model periodic behavior or we want to model a trend and so on. Somehow it sounds like the clustering that, we say we want to have 3 clusters and then we use data to learn the parameters. This is a confusion that you might have, but inherently state space models are in supervised learning. Now let's back to developing our model. It is common in probability that we represent the probabilistic model with functions. We can define 2 functions that each represents one of those probabilistic models. The first one is denoted by h, and it represents the observation model. Actually, it maps the underlying dynamics to the observations. And the other one is shown by f, and it represents the evolution of the underlying dynamics over time, let's say from time t-1 to the time t. Like any other probabilistic models, we need to consider the error terms. And here, v and w represent the error variables, and each of them corresponds to one of those models. Now we have the model and the framework to work with. We can ask another 5 questions, and answering these questions will lead us to the Bayesian dynamic model, or BDLM. And these questions are: what are the functions h and f? What are the hidden states variables and how can we define them? What are the error variables v and w? What is the algorithm we can use to carry out the recursive process? And finally, what is the learning process about? Now let's answer these questions one by one. Now we get to the point that we can present BDLM. BDLM is a special case of a state space model, where all the variables are Gaussian and all the relationships are linear. Mathematically, it is represented by two linear equations. The first equation is Cx plus V. In BDLM, V is a Gaussian distribution with mean 0 and the covariance matrix R. C is called the observation matrix. It is a matrix that determines how the underlying dynamics are superposed to generate the observation. The second equation is Ax plus W. And again, in BDLM, W is a Gaussian distribution with mean 0 and the covariance matrix Q. Here, A is called the transition matrix. It is a matrix that determines how the underlying dynamics are evolving over time. Collectively, we call these predefined matrices C, A, R, and Q as the model. Also, for each model, we have some parameters that are related to these matrices. Up to now, two equations are answered. We know what are the functions and we define the error terms. Let's see what are the hidden state variables. Okay, let's recall the equations we have developed until now. You see, we have a model with four matrices C, R, A, and Q. These matrices can be defined based on the underlying dynamics. The figure shows the whole model matrix building process. On top, you see the hidden state variable shown with the bold X, and the observation is shown by the bold Y. Underneath, you see the icons we use for the underlying dynamics. Depends on the underlying dynamics you want to include in the model, you can pick one or some of them. The arrows show the variable contributes to the model matrices. Here, LL is a local level, indicates the baseline behavior. LT, or local trend, shows the trend. P indicates whether you want to have periodic behavior or not. And the AR shows the time-dependent error in your model, which is the autoregression model. This error is different from other errors in the sense that this component captures the phenomena that exists in the model, but you didn't consider them in your model. You will see an example of it in the next section. Just as a refresher, C is the matrix that determines how the underlying dynamics are superposed to generate the observation. The A matrix determines the evolution of the hidden state variables, and the R and Q matrices are the error covariance matrices. Let's look at a very simple example. Imagine we have a time series and we want to model it only by using a constant local level. Then the equation is reduced to y equal to 1 multiplied by xll plus v. And the transition model will be xll at time t equal to 1 multiplied by xll at time t minus 1 plus w. And here the model is going to be 1 sigma v squared and sigma w squared. And these two sigmas, they are the standard deviations of the observation and transition errors. And here the parameters is going to be these two standard deviations that we're going to learn them from the data. So as you can see, depends on what kind of dynamics you want, you can extend these matrices to build the global model matrix. Up to now, 3 questions are answered. The next questions are, what is the recursive purpose and what is the learning aspect of the BDLM? We already talked about the recursive process. In the case of BDLM, there is an algorithm called Kalman filter that allows us to perform this process. KF is an algorithm that uses a series of observations to estimate the hidden states by building a joint probability. KF allows us to carry out our estimations between time steps. Here in the figure, you see that we have the estimation between t minus 1 and t, and the Kalman filter allows us to move to the next time step between t and t plus 1. It also helps us to move backward. This property allows us to not only go through time, but also go back through time to estimate the initial conditions. Now, the remaining question is that what is the learning process in the BDLM? When we select our components to model different behaviors, we will have some parameters that need to be estimated, like the standard deviations that you saw in the previous simple example. Here, we can use the maximum log likelihood estimation. In other words, we want to find a set of values for which the parameters going to maximize the log likelihood of the function. And the good news is that when we are using the Kalman filtering, we have this log likelihood function, which is a function of all of these model matrices, and we can use it to find these parameters. Okay, we completed our questions, and now we have a fully defined framework to analyze the time series. In summary, we have a system responses, and the purpose of the BDLM is to decompose them into the underlying dynamics. We can have different components that each determines a particular behavior. For example, XLL is a baseline behavior, XT is a baseline rate of change or speed, XP is a periodic behavior, and XAR is the behaviors that we haven't modeled it in our model. And it's like a bin that we put the rest of the phenomena inside it. In this presentation, I use the OpenBDLM for the case studies. The OpenBDLM is an open source new tool that you can carry out all the procedures I explained. Okay, the first case study is the air temperature data. For this data, we consider we have a baseline, a trend, an annual periodic pattern, and an autoregressive component. So basically, we want to extract three basic dynamics from this data. You see the results we obtained from the time series analysis. In this figure, the black line is the mean value and the green area is the confidence interval, which is the mean plus minus 1 standard deviation. On top left, you see the local level, which is a baseline behavior. It shows a negative slope, meaning that the mean temperature is decreasing. On the bottom left, you see the speed of the temperature over 2 years, which is locally constant. The baseline measurement is in degrees of Celsius, and the speed, of course, is going to be degrees of Celsius per day, which is here is around -4 E-3 per day, and it is equivalent to -1.5 degrees of Celsius per year. In other words, we can say that after 2 years, the temperature dropped approximately 3 degrees. On the top right, you see the annual periodic pattern, and in this case, it is a fluctuation of the temperature in different seasons. On the bottom right, you see the autoregressive process. It shows time-dependent errors. You see that it is stationary and there is no other significant pattern in the time series data. The second case study is the volatility index data, or VIX. It shows the global volatility of the stock market. For this data, we consider we have a baseline, a trend, and an autoregressive component. So basically, we are looking for two dynamics from this data. You see the results we obtained from the time series analysis. In this figure, again, the black line is the mean value and the green area is the confidence interval, which is the mean plus minus 1 standard deviation. On the top, you see the local level, which is a baseline behavior. It shows a negative slope, meaning that the mean index value is decreasing. Underneath, you see the speed of the index over 2 years, which is locally constant. The value is equivalent to -3 units per year, which it is approximately 6 units for the 2 years. On the bottom, you see the autoregressive component. Even though it is stationary, you can identify some patterns inside the data. There are two possibilities. Either there is a periodic pattern inside the data, such as the holiday effects or some other effects. And the second possibility is that maybe the trend is not locally constant And of course, the dynamics we defined cannot capture this non-constant speed behavior. In this case, we need to refine our model to include the speed rate of change or acceleration. However, the model needs to address our objective with respect to the decision-making process. For example, here we want to see the rate of the decreasing over 2 years so we can decide for the future and we address this objective. Or for example, we want to see the overall baseline behavior of the market volatility. So choosing the components to model our data, it depends on our objective. Speaking of the future, it is interesting if we can investigate our model prediction capacity. The figure shows the model prediction capacity. On the top, the data are divided by a vertical line as of July 2014. The gray part on the left is the time when we trained the model, and the blue line indicates the test set for 1 year. The solid black line is the mean prediction, and the green area is the confidence interval. As you can see, the model captures the periodic behavior of the temperature. However, the short-term periodics are not captured. To model such short periodics, we need to add additional periodic components with shorter periods. The figure on the bottom shows the metrics we use to investigate the predictability. The blue line is the mean squared error and the orange line is the squared correlation coefficient. In general, the lower the squared error and higher correlation, the better the model is. You can see that as time goes, the correlation and MSE reach a plateau. This indicates that the model is suitable for long-term prediction. Because you see that at the beginning of the testing time, the correlation is low, and as time goes by, the correlation is going to increase. We did the same thing and same investigation on the VIX data. As you can see, the model predicts a decreasing trend for the whole year. But the time series shows an increasing trend and then a decreasing one. This can be seen clearly through MSE and R squared. For a short period of time, there is a low MSE and high correlation, but it vanishes very rapidly. So we can say that this model is good for short-term predictions. And after almost a year, you can see the correlation is almost zero, even though both the prediction and actual data show decreasing trend. So this indicates that we need to define additional behavior to model the acceleration, as I mentioned before, or perhaps there is an anomaly here and we need to use advanced BDLM procedures to model this kind of anomaly, such as switching Kalman filter. Up to now, we see the capability of BDLM to decompose the time series data. It is a good idea to compare the BDLM with another approach such as the one introduced recently by Facebook, and it is called Prophet. For a single time series, the model is a transformation of certain time covariates and an additional error. The error is a normal distribution with a mean 0 and the standard deviation of sigma v. However, the C matrix here is not a fixed scalar. Instead, they are nonlinear functions, or we call them operators. And each operator models a certain aspect of a time series. For example, LG is for non-periodic patterns, LS is for periodic patterns, and LH is for the holiday effects. You can see the model as a combination of 3 simultaneous nonlinear regressions. In other words, the whole model is a curve-fitting problem rather than a 2-step recursive model such as the one we have in BDLM. So it's a good idea to compare it with BDLM as well. Here we have the BDLM model for a single time series. As you can see, first there is no transition model. In BDLM we have a recursive process that evolves over time, but in Prophet we have a single shot curve-fitting objective. Second, the transformation in BDLM is linear. However, in Prophet, these transformation or these operators, they are nonlinear functions. Okay, let's take a look at the results obtained by Prophet. We carried out the same prediction capacity investigation using Prophet. The Prophet successfully captures the periodic patterns of the temperature data. It also captures some short-term variability of the data. It is because of the nonlinear functions used in the model that increase the flexibility of the model. In the case of the BDLM, we need to add additional periodic components for short-term phenomena. In terms of MSE and R-squared, Prophet shows a low MSE and high correlation for long-term predictions. Here you can see the results for the VIX data. You notice that the model prediction capacity is very poor. This can be seen within MSE and R-squared as well. High MSE indicates a significant accumulation of errors and zero correlation. Even for the short-term prediction, the model acts very poorly. On the side note, I have to mention this, that in this presentation, we do not compare the superiority of the BDLM and Facebook Prophet. Rather, this presentation aims to give you the insight of different time series modeling. And I need to add it on top that choosing the model depends on your objective and answering some questions, such as what is the trend of the data? Is there any periodic pattern? Is there some other dynamics that we can't see? Okay, up to now, we introduced the BDLM, we modeled two time series data sets, and we compared it with another time series modeling approach. But I need to say this, that one of the advantages of the BDLM is related to the simulation of the data, which is called sim to real. And this means that once we have the data-driven model of the time series, we can generate new time series. So we can define the sim to real as generating new time series from the underlying dynamics characterized by the M, which is the model matrices. The figure on the right shows the concept graphically. Given the hidden state variables, we want to generate new time series data. And you can see here, such realizations can be useful in other analyses when we don't have access to a very large data set. And I have to mention this, that the underlying dynamics ensures that the new realizations mimic the underlying dynamics of the actual or real time series data. Okay, in this presentation, we showed the capability of the BDLM in decomposing time series by generic components. To wrap up the presentation, let's talk about the 4 research directions of the BDLM. Of course, the first direction is to create new components, such as kernel regression to capture non-harmonic yet periodic phenomena, or more advanced components using recurrent neural network, such as LSTM. The second direction is related to multiple time series. We have situations that we might collect different measurements from the same system dynamics. For example, the sensors that we have on a bridge. We can extend the BDLM to create these dependencies between the different time series data. Another direction is regarding the kinematics of the data. Here, we basically use the Newton kinematics to model the baseline and the speed. We can extend such kinematics so we can model different regimes using acceleration, with different trends, with different accelerations as well, such as the one that you saw in the VIX data. And the last but not the least, we can extend the BDLM for different types of estimations. These type of estimations, one category of it can be online versus offline. In this work, we used offline methods. It means that we have the data beforehand. Now we can develop methods to estimate the underlying dynamics of the system as data become available in an online fashion. Also, here we assume the transformations are linear. We can extend the BDLM for non-linear cases, such as extended Kalman filter. And finally, we might want to use other types of distributions for the variables rather than the Gaussian that we use.